Welcome back to Chapter 1.3, Part 10 of 11. In Part 9, we drew two warnings about consistency. We have computed two summaries of the sampling distribution, its center and its spread, but never seen the object itself. In this part, we name it. Then, fake the universe on a computer. We redraw the sample thousands of times and watch the summaries we proved on paper appear in front of us. We have been talking about the distribution of X bar across all possible samples as if it were a real object. It is, and it has a name. The sampling distribution of an estimator is the probability distribution of the estimates you would get across all possible samples of a given size n from the population. Here is the conceptual core of the whole chapter. In real life, Priya gets one sample of 200 claims, and therefore one estimate, X bar, equals 8,410. She can never see the sampling distribution because she only ever draws once. But in a simulation, we are gods. We know the true population, so we can draw a fresh sample of 200, compute its X bar, write it down, throw the sample away, and repeat 10,000 times. The 10,000 X bar values we collect are a picture of the sampling distribution. We are watching the random variable X bar do its thing over and over instead of seeing it just once. Let us build it. We model individual claims with a right-skew distribution, a log normal, the standard rough model for insurance losses, many small claims, and a thin tail of catastrophes, calibrated so the population mean is $8,000. We write a function that draws 200 claims, averages them, and repeats 10,000 times, collecting the means. Two lines of the output deserve a standing ovation. First, the mean of the 10,000 X bar values lands essentially on $8,000. The sampling distribution is centered on mu, exactly as the unbiasedness proof promised, now seen, not just arrived. Second, the standard deviation of those 10,000 estimates matches sigma over the square root of n from part 4. That standard deviation of the sampling distribution has its own famous name, the standard error, and the simulation shows you literally what it measures, the typical sample-to-sample wobble of your estimate. The formula and the histogram are two views of the same object. To summarize Part 10, the sampling distribution is the distribution of estimates across all possible samples of a given size. Priya can never see it because she draws only once, but in simulation we redraw 10,000 times and the cloud of estimates is the sampling distribution made visible. Two facts we proved on paper now appear in the output. The mean of the 10,000 estimates lands on the true mean, confirming unbiasedness, and their standard deviation matches sigma over the square root of n, the standard error. Formula and histogram are two views of one object, but we have only confirmed the center and the spread. In Part 11, the finale, we look at the part the formulas cannot give us, the shape of the distribution, and how it transforms as the sample grows.